Hello, Mr. Newman here, and today we're going to learn about limits. I'm going to introduce you to the notation of a limit, and we're going to look at some graphical limits, and I want to build an idea of what a limit is. So let's get started. First of all, I'm going to give you this function right here. Notice this function has the factor x minus 1 in both the numerator and the denominator. What that does is that creates a whole. Okay, now we're going to learn more about this feature in the future, but right here on the graph, you guys can see that right at 1, 2, the line actually doesn't exist. And it should be pretty obvious that when you try to plug in 1, see there's the hole, when you try to plug in 1 into the function, you get 1 minus 1 in the numerator and 1 minus 1 in the denominator, which means you're dividing by 0, and since you cannot divide by 0, that function is going to be undefined. Now, even though the function does not exist at 1, 2, if you look at the graph, you can look and see that if we were to fill in the hole, if we were to plug it in, then we would totally get the y value of 2. But the problem is there's no way for us right now to figure that out algebraically because you try to plug in 1 and you don't actually get the number 2. Well, this is where limits come in. What a limit does is it looks and it says, okay, what if we get really, really close to that value? So, for example, what if we plugged in the x value of 0.9 into our function? Well, when you plug it in, you could try this on the calculator, but you can also trust me that plugging in 0.9 will give you 1.8. Then we want to plug in another number that gets even closer to 1, like 0.99. If you plug that in, you get 1.98. And what if we plug in 0.999? Well, you plug that in, you get 1.998. Hopefully it's obvious to you that this is getting closer and closer to our y value of 2. However, if you actually plug in 1, you'll get undefined. So what a limit is a limit says, what is the value of y as x approaches 1? A limit does not actually care what the value is at that function. It only cares what is the value, the y value, as the x gets closer to that number. And in this way, we can plug in the whole and figure out what it's equal to. You can also do this, notice these values get closer to 2. And so as x approaches 1, we say y, or f of x, is equal to 2. On the other side, and notice as I'm plotting these here, see, the points get closer and closer to 1, 2. This is, of course, approaching from the left side, going right, as we get closer to the hole. On the other side, we could plug in numbers such as 1.1, which would give you 2.2, 1.01, which would give you 2.02, and 1.001, which would give you 2.002. Notice these numbers are also getting closer to 2, but from the other side. So again, even though you plug in 1, and that's undefined, we can say what happens as x approaches 1. Now, I'm going to show you this notation later, but just so you have this posterity, if you're approaching from the left, you would put a minus, like that. Notice it looks kind of like 1 to the negative power, but that doesn't make any sense. So this is actually a special notation only used in limits. As x approaches 1 from the right, however, from the positive side, we actually, in this case, get the same y value. Those numbers, 2.2, 2.02, 2.002, are getting closer and closer to 2. And the points on the graph look like this, the red dots. We're approaching that same one from the right. So this is how you write the limit. Okay, you say, first of all, the limit of a function 2x times x minus 1 over quantity x minus 1 as x approaches 1. So you always write a variable first. That is always the variable that is approaching the number. And that 1 is the value we're approaching. This over here on the right is always the function. So it's typically read the limit of the function as x approaches 1. The approaches is an important idea because it means that we're not actually evaluating at 1. Notice if you plug in 1, you don't get a value. But we can figure out what's it getting closer and closer to. One way to do that is to make a table on the calculator or a table by hand, and you see that they are getting closer and closer. Another way to do that is to look at graphs, and we're going to look at that in just a moment. Let's evaluate some of these though, because you want to know how to evaluate these when the value is not a problem. Now, what do I mean by that? In other words, that function up above, right here, 1 is a problem because it's not in the domain. You can't actually plug in 1 into the function. But there are tons of limits where the limit is simply the value at that point. When does that happen? Well, that happens when the function is continuous. What the heck does continuous mean? It means that there are no jumps, no breaks, and no holes, okay? This function, the first one, had a hole, so we couldn't use this rule. But if there are no holes, and if there are no jumps, and if there are no breaks, then what can you do? You can simply plug in the value that x is approaching. For example, this first one, notice how it's x squared. We are approaching the value of 4. So we can just plug in 4 here. Notice that gives us 16, right? So the function, as you get closer to 4, gets closer to 16, which makes sense because it is 4 at 16. This function is linear, of course. Again, we're approaching 4, so you can just plug 4 in to 5x, and you get 20. Over here, the next one, notice that this function is approaching 4, but 4 is not the issue. And 4 is not the value that is not in the domain, right? What is the problem value? Well, the problem would be is if you tried to plug in 0. But we're not trying to plug in 0, we're trying to plug in 4. So we can just plug in 4 and we get 2. Over here, there's a square root function. Notice you can't take a square root of a negative, but we're not trying to plug in a negative, we're trying to plug in 9. You can simply plug it in. So the limit as x approaches 9 of the square root of x is 3. And then for these last two, here we're approaching negative 2. You can also approach negative values. You plug in negative 2 and you get the y value of 2. And for this last one, the limit as x approaches 3 of that function, we'll simply plug in 3 and you get 49. All right, let's talk about times when the limit doesn't exist, because there are times when the limit will not exist. For the first function here, these are example functions, okay? These 3 rules are very general, okay? So here, notice our first function is one of the parent functions you should have had memorized. Part of the reason this is important in calculus is because this is an example of a function where the limit does not exist at a certain point. So the first situation is when the function approaches a different number from the right and the left. Sorry, when the limit approaches a different number from the right and from the left. So if we're approaching 0, notice the limit as x approaches 0. If we're approaching 0 on this first function here, we're approaching 0 on the right, get closer to 1, but on the left, you get closer to negative 1. For that reason, since the sides are approaching a different y value, one side's approaching negative 1, the other side's approaching 1, then here the limit does not exist. So we write DNE for does not exist. This middle one here, this function, is another situation. This is where a function increases or decreases without bound. That means that it keeps increasing and you can't set an upper limit or a lower limit to it. So here in the middle, as we get closer and closer to 0, notice that on the left side, it keeps increasing. On the right side, it keeps increasing. Now these might be approaching the same infinity, but because they're increasing without bound, then this limit is not going to exist. So we write D and E. For this last one here, this is an example of a function that oscillates between 2 fixed values. That's the third situation where limit does not exist. Now notice I did change this on you. Whoops. We're approaching infinity here. And so in this situation, we're asking what happens as the function keeps going to the right. Does it ever settle on a given point? This is including in limits at infinity that we're going to learn about in a later video. But the basic idea is sine keeps going up and down and up and down and up and down. It doesn't actually get closer to a single point, a single y value. So because of that, this function oscillates between 2 fixed values. And so it will never actually reach a limit. So in this case, the limit does not exist. So we write DNE. All right, now we're going to look at how to evaluate limits graphically. And you need to pay careful attention because a lot of these are not completely intuitive. Here, this first one, we have x approaching -4. Now, we're looking at this function first, so ignore the g of x on the right. We're just looking at f of x. And so what we need to do is we need to look at what happens from the left of -4. Notice it's when x is -4. And from the right. Are those two values approaching the same place? Well, yeah, the function is getting closer to 2 from the left and from the right. Because those are the same, the y value is going to be 2. So the limit as x approaches -4 of f of x is 2. Notice, however, this is an open circle, so that does not have any bearing on what the limit is. It does, however, affect what the function is. So if I were to try to evaluate f of -4, we would write that it is undefined. Notice that undefined is different than DNE. Limits do not exist, but functions are either defined or undefined. And if they're defined, they are a certain value. Okay, let's look at the limit as x approaches 1. Well, here, from the left, it's approaching the y value of 4. But from the right, it's approaching the y value of -2. Because those are different, this limit does not exist. But the function at 1, if you were to plug in 1, it's a filled-in circle up there at 1, 4. So therefore, the function is equal to 4. So you can have times where the function does exist, but the limit doesn't. And you can have times where the limit exists and the function is undefined. For the number 4, notice that there are no filled-in points. Well, remember, a curve is just a bunch of points. So are these two sides approaching the same point here in the middle? Well, yes. Even though there was not a point drawn there, we know that there is a y value because there's no open circles drawn. And so it approaches -2 from the left and -2 from the right. So that value is going to be -2. So the limit as x approaches 4 is -2. Likewise, the function there, f of 4, is -2 because it exists at that point. For 6, we're approaching the left and the right. And so here, we're getting closer and closer to the y value of 5 when you ignore the whole, ignore the exact value. So that limit is going to be 5. But the function itself is equal to 2 because there's a point down there at 6, 2. Go ahead and try this next one to see if you understand the idea of the left and right being the same and the idea of the function existing either at the same place or a different place. All right, welcome back. Let's check your answers here. So for -2, we're approaching the left and the right. Those are different, so therefore the limit does not exist. But at -2 for g of x, that is -2, 2. So therefore that y value will be 2. As we approach 0 from the left and from the right, we're getting closer and closer to the y value of 1, so the limit is equal to 1 because the left and the right are the same. And at that point, the y value is also 1, so g of 0 is 1. As we are approaching the x value of 3, as x approaches 3, the left and the right are both going towards the same place, so therefore the y value is going to be 0, so the limit of g of x as x approaches 3 is 0. But when you try to plug in 3, you get that point that's filled in down there because the open circle means it doesn't exist at that point. So we get -1. Thank you all for watching.